Hello everyone, my name is Nikunj and I am a PhD student at the School of Chemical Engineering at University of New South Wales. I am working under the supervision of Dr. Francisco Trujillo, and my project is on the development of ultrasound and infrared radiation assisted atmospheric freeze dryer. So let's get some brief overview that what is drying actually. So when we harvest the food produce, it has a very high moisture content. So if we store this high moisture content food produce for a longer time, there can be a growth of microorganisms and several various chemical degradation over the time. So it is a big problem, right? So how we can mitigate this problem? So one of the ways to dry. So drying is a basically process to remove the water out of the food product. And by doing so, we are extending its shelf life. So currently there are various type of drying methods available, such as vacuum freeze drying, vacuum drying, spray drying, and various other drying. So selection of particular drying method to dry your food product is depends on the final desired properties that you want in your final food product, right? So now question comes that why this drying is so important. So by looking at this graph, you might get the answer. So at left-hand side, you can see the graph of the energy consumed by the various sector globally, like transportation, electric power generation, and industrial sector. So industrial sector consumes around 27% of total energy globally. And drying operation alone consumes total of 25% of this industrial sector. So drying is a very energy intensive operation, and there is a need to innovate a drying technology which can be which will be a energy efficient method. While selecting the drying for particular product, we need to account several aspects of the process. First is quality aspect, and second is economic aspect. So if you want a quality aspect in your food product, like you want your quality of the food product should be retained throughout the process, then we should go for the vacuum freeze drying, because vacuum freeze drying can retain your quality aspect such as food texture, sensory attributes, and nutrient throughout the drying process. While if we are worried about the operational or economic aspects, then we should go for hot air drying, because here the operational cost and processing time will be minimal. But here, hot air drying will fail in maintaining the quality aspect of the food product. But what if we want quality as well as economy of the process? At this point, atmospheric freeze drying can help us. So what is actually atmospheric freeze drying? So to understand the atmospheric freeze drying, we have to understand what is vacuum freeze drying. So here in left-hand side, you can see the phase diagram of water. So point A in this phase diagram represents the starting point of vacuum freeze drying. So in vacuum freeze drying, we take the food product, we freeze it first, and then we expose it to the vacuum. So due to the exposure to the vacuum, the water present in the form of ice inside the product will directly convert it to water vapor during by sublimation process, and we get the drying. But applying the vacuum can be causing the very high operational cost and very long time for the operation. So in atmospheric freeze drying, we don't use vacuum. Yes, freeze drying can be done without the vacuum. In 1959, it has been observed that for freeze drying to occur, you don't need vacuum, but you just need the high difference between the water vapor pressure of the product and water vapor pressure of the drying air. In simple words, if you have very cold and dry air and you pass it to the frozen product, you can still get the drying. In right hand side, you can see the schematic representation of atmospheric freeze drying, where the cold dry air will be flown from the frozen product, and the water in the form of vapor will come out from the product matrix. Now, let's have a look on the history of AFD. So as I said, in 1959, it was first observed by the Dr. Merriman that you need only a cold dry air to freeze dry any product. So from that point of time, this AFD field was innovated, and throughout the years, many experiments was carried out. So After some time, some AFD studies was carried out on the liquid foods such as milk, coffee, and juices. In 1990, first energy consumption comparison was carried out between the atmospheric freeze drying and conventional vacuum freeze drying. And it has been observed that if we apply AFD on an industrial scale, it can reduce the energy consumption by 20 to 30%. In late 2000s, more research was focused on the development of various innovative systems to execute this AFD. Throughout this period, various different systems was innovated, such as fluidized bed drying process, spray freeze drying process, tunnel freeze drying process, and vortex tube-based freeze drying process. In the last decade, the main focus was given on the advanced technology integration with the AFD to accelerate the drying rate. So the major problem in AFD which we face is the very slow drying rate. So in the last decade, various researchers have integrated various advanced technologies such as infrared radiation, ultrasound, and microwave radiation to accelerate the drying rate during the AFD. The major focus was given on the ultrasound. Fine. So ultrasound is a non-thermal tech. It doesn't involve any application of heat, and the application of ultrasound will not impact the quality parameters of the food product. So now let's look how ultrasound can be applied in the AFD. So there are majorly two ways that we can apply ultrasound inside during the AFD. First is airborne ultrasound, and second is direct ultrasound. So majority of studies that have carried out on AFD was carried out with the airborne ultrasound. And it has been shown that in airborne ultrasound, it can only utilize 20% of energy that we are putting inside the process. This is like very high loss of energy. But why there is a very high loss of energy? So if you see here, in airborne ultrasound, ultrasound waves is transferred via the air to the product. Like this is the ultrasonic transducer, and the sound waves are coming through the air and reaching to the product. So during this process, what happens is when sound waves transfer from the one medium to the another, here in the case, which is sound waves transfer from the solid medium to the gaseous medium, and then again to solid medium. So this result in the high difference in the impedance, and which ultimately results in the high energy loss. So it is a big problem, right? So this problem can be solved by simply using direct ultrasound. In the direct ultrasound, the sound wave will not change the medium. It will transfer from solid to solid, which means a low difference in impedance and ultimately low energy loss. But there is no study has been carried out using direct ultrasound in AFD. So this is the research gap that we are going to fill. So to fill this gap, we have hypothesized our objective, which is application of direct ultrasound in the AFD can enhance the water diffusivity, and which will lead to improved drying kinetics and improving the quality of the food product. So to prove the hypothesis, we have designed three research objectives. So first objective is the modeling and fabrication of AFD prototype. So here we will use console multiphysics software to simulate various multiphysics involved in the process to make the prototype which can execute this ultrasound assisted atmospheric freeze drying. After the building of prototype, we will analyze and optimize the AFD process for Apple, and we will analyze the drying kinetics, physical chemical characterization, and will compare our AFD process with the conventional hot-air drying methods and conventional vacuum freeze drying. In the third phase, we will choose another food product with the different physical characteristics. For this project, we will use eggplant. Why eggplant? Because eggplant has a different physical property. It has a high porosity compared to apple. So we want to analyze that how our AFD will perform with the different food product which having a different physical properties. So far, if I talk about the current progress of the project, so we have successfully built the prototype of the AFD, and currently we are studying the drying kinetics of the apple. So far, we have achieved over 95% ultrasound power transmission efficiency, which is way higher than previously reported transmission efficiency, which was less than 20%. And if I talk about the drying time reduction, so during the ultrasound application, we got 10 to 20% of drying time reduction. And with the application of infrared radiation, we got around 33% of time reduction for drying. So what will be the benefits to the industry while adopting this technology? So if you look at the Australian dried fruit and freeze dried food market in the Australia, so we can see that the dried fruit market is was standing at 89 million US dollars in 2023, and which was expected to grow at a 6% CAGR, while freeze dried food market of Australia was standing at $36 million in the 2023, and which was expected to grow at 8.7 CAGR. The major constituent of this freeze-dried food product market was fruits, vegetables, and ready-to-eat meals. These are the same product that our technology was targeting. So while adopting our technology, Australian food industry can get various benefits, such as consumer acceptance, cost saving by saving the cost on the operational side. It can foster the global export by exporting the value-added Australian dried food products to the foreign countries. And while last not the least, it can reduce the GHG emission involved with the highly energy-intensive drying processes. So with this, I'm ending my presentation. Thank you to FFS for opportunity to present my research amongst the people.